Hello, everyone. My name is Beata Koenig, and today I am truly honored to have the opportunity to talk with Professor Reinhard Genzel, a German astrophysicist, co-director of the Max Planck Institute for Extraterrestrial Physics, who in 2020 was awarded the Nobel Prize in Physics for the discovery of a supermassive compact object at the center of our galaxy. Professor Genzel shared the 2020 Nobel Prize with Professor Andrea Ghez and Professor Roger Penrose. Good morning, Professor Genzel. Thank you so much for joining me today.
Good morning. Good morning.
So there is a supermassive black hole at the center of the Milky Way, and it's called a Sagittarius A star. But as far as I know, it took many decades to determine that this supermassive compact object was in fact a black hole. And first of all, I would like to ask you to tell me a few words about how the story began and what were the major obstacles that hindered observations along the way?
Well, of course, the story developed 100 years ago with Einstein's presentation in Berlin of the theory of general relativity, which basically united what we knew before from Galileo and Newton and Kepler with the fact that light can also see gravity, which was not incorporated in those earlier theories. And also that light is the fastest way of communication in the universe. Nothing can go faster than the speed of light. And that immediately, once you have that, light can see gravity and nothing can go faster than the speed of light, brings you theoretically to the concept of a black hole. Because if you make anything so massive or so compact or both, that the escape speed, so to speak, becomes comparable to or greater than the speed of light, well then the inner volume of this region cannot communicate anymore with the rest of us. So that was clear theoretically in the early 2000s, but not much happened for another 50, 60 years. Theory happened, more understanding happened. Solutions were found mathematically for how such object would look like. It became clear that at least conceptually they're very simple. You know, they just have a mass. They can rotate. They can have an electric charge, but that's it. No hills, no shapes, if you like, But then the question was, how would you see that? If you have something where light cannot escape, how would you see it? And the answer became all of a sudden pretty clear when the so-called quasars were discovered in the 1960s. The radio astronomers at that time were discovering radio sources all over the sky, and then they would, ask their optical astronomy colleagues, tell us, look in this direction, tell us what this is. And in some of these very spectacular radio sources, it turned out that this looked in the optical like a little faint star, variable, and with properties of the light, which we call redshift. In the spectral lines, redshifted, initially the first one was 16%. Everything redshifted 16% to the red. And of course, at that time already was clear that the universe was expanding. And in that expanding universe, the further away something is from us, the more redshifted the radiation is. So that was clear. So a number of theorists working on that problem basically said, well, if this is really due to the expansion of the universe, this object must be hugely distant. We're talking about billions of light years. And so when you then take the little measly star and convert its radiation into what we call a luminosity, the total energy output, you come up with huge numbers, thousands, 10,000 times the radiation output of the entire Milky Way, all in a little measly star. How can that be? And now comes the paradox that a number of theorists had the idea, well, okay, you know, can't be the same processes in the sun, fusion from hydrogen to helium. It must be something much more efficient. And here comes in, you know, black holes remarkably, and general relativity, because you see, Einstein had already in the special theory of relativity explained that mass and energy are equivalent. So if you have a certain amount of energy, then that's equal to a mass times c squared, where c is the speed of light. And vice versa, if you take mass and you let it fall into a black hole, before it disappears behind the event horizon, you can convert the rest mass energy, or a significant fraction thereof, into radiation. So that was the idea. It's a paradox. Black holes, everything disappears in it, but before you disappear, you can be very bright. That was the idea. And then the question, of course, came, how would you prove it? Yeah, you can say whatever you like in the sciences, you have to prove it. And that is really the tricky thing, because these quasars, as spectacular as they are, they're hugely distant. So how would you make an experiment to see what you can see? Well, you look for the action of gravity onto objects in the vicinity. That's the idea. Like the planets around the sun. So if you replace in the solar system the sun by a black hole of the same mass, well, the planets would still go around the sun in orbits. And so by measuring then the orbits of the planets in that system, you would come to the conclusion, well, there has to be an object in the center with one solar mass, okay? The only difference is in that system, the sun doesn't shine, okay? But it's the same kind of an idea. So why can you do this with quasars? Not at that time, they were too far away. So then you need one more step to sort of get to the beginning of my story, which is two theorists in the United Kingdom, Martin Rees and Donald Lynden-Bell, speculated that maybe, you know, these quasars, centers of galaxies, very far away, are very rare states of accretion of material onto black holes. But could it be that not only a few, but all galaxies had a black hole in them? If that were the case, well, maybe also nearby galaxies could have a black hole in them. Well, even our own galaxy could have a black hole in it. That is what they wrote down in 1971. And basically in there, it was sort of said, now you observers go ahead and observe, you know, see whether you can find a compact mass, say in the galactic center. That's how the story started. Now there are still some technical issues all throughout this story, which now happened for 40 years. To actually get the evidence, you cannot do this in the optical. You have to go to the so-called infrared band because there's dust between us and the galactic center. And you have to measure hugely precisely to see actually motions or something, hugely precisely, because these black holes, while they're powerful and very massive, you know, they're very compact. And to distinguish, to exclude, if you like, that the alternatives which you could think of other than a black hole, you have to measure very, very close as you can, preferably even at the event horizon. Not inside of the event horizon, because then you can't come out again, but just outside. And that took 40 years, ever more technology. You see, over that period, and I got into it about a few years after this sort of whole thing started. I was a postdoc in Berkeley, working with a very famous physicist who had gotten the Nobel Prize for the invention of the laser and the maser. And he then had moved to California and was interested in astronomy, and he knew how to build infrared spectrometers, as we say. So you could, basically spread the light, and then you begin to look at spectral lines, and from the position of the spectral lines, you can learn something about the motion of a gas cloud. And that's how we started in the late 70s, early 80s. And after about 6-7 years, we had the first evidence, actually. It's pretty much the same evidence we have now, that there is an object of 2 to 4 million solar masses in the very center of the Milky Way. We could pinpoint it. There was also this radio source there, which also had been just discovered. And so we were pretty convinced by 85, well, that there could very well be a black hole. Well, but nobody else believed it. You see, that's the story of scientists, especially physicists. They really want to know it very well and exactly, and you can tell them a story and they say, nah, there could be all kinds of other stuff in there. Yeah, well, why? Well, because we were measuring these gas motions on scales of light years, and that's 1 million times away from the event horizon. So you could put in, faint stars instead. You could, neutron stars had been discovered at the time. Some people said, well, maybe it's a cluster of 1 million neutron stars. How do you know? And so we knew we had to, and there were also technical issues having to do with the fact that we were looking at gas, and gas, the gas does react to gravity, but you can push it around with magnetic fields and other forces. So people were a little skeptical that what we had was good enough. And so then really it took several phases of 10 years to improve the technology. First, we needed to measure stars instead of gas. Then you improved the sharpness of our images by a factor over time of 10,000. And in the end, indeed, I would say we were always making progress. And the number of people who would believe that we actually had a case was getting every 10 years substantially more. Okay, but then it took, and then Andrea joined also. And so this was also very good, because another principle of science is that it should be repeatable. It shouldn't be just one group. So that was very good. But still, it took until, I would say, around 2002 or 3, until most of the people would say, this looks very, very likely. It was still not, it was still not in that sense exclusively necessary, but it was very likely. And so then we made another step. Instead of a single telescope, we then had the idea to combine the light in the infrared of 4 8-meter telescopes in Chile of the European Southern Observatory. A very, very challenging experiment, very challenging. Took us about 10 years to build that piece of equipment, but we had in the meantime seen a star which is on a very elliptical orbit, and in 2002 had approached the radio source to 17 light hours. That was absolutely not expected. 17 light hours is the same as about 3-4 times the orbital radius of the planet Neptune. So we are now, we are making measurements on solar system scales. Now, that star at that point was moving with about 2.5% the speed of light. A sensation, okay? And so then, if it doesn't matter whether you take Kepler or Newton or General Relativity, you get the same answer, which is there has to be an object of 4 million solar masses. And now you're so close that indeed, as long as General Relativity is correct, that looks pretty convincing. So were we done? No, because then people came and actually started challenging General Relativity. They said, well, how do you know that on these kinds of gigantic scales, which had never been tested. GR is actually correct. Now, here comes the sort of the persistent scientist. You have to then say, well, what can you do? Well, you can measure better with this interferometer, and then you can do it again, because that star took 16 years to go around. So when you're done with building your new instrument in, say 15 years, well, then you can test general relativity. That's what we did. And now you can question, are we done now? Almost, but still not quite, because we've now measured the mass of this object to a fraction of a percent. It's very, very clear that there is a compact object, but you see the Nobel Foundation didn't say discovery of a massive black hole. Yeah, it didn't say that. Well, in the explanation of the prize, it does say it, okay? But in the top title, it says supermassive object. So there's a little hole still, because we have not yet shown that general relativity is correct at the event horizon of that object. But we are very, very close. We are, and also now we have another team trying another technique, which is using light and using the light bending, again, to measure the strength of gravity, and everything looks very good. What we haven't measured is how fast the object spins, rotates. That we want to still do. And then once you have rotation and mass, then, as I mentioned initially, the general relativity postulates that you need nothing else. Okay, these are the two numbers you need. And so then you can, if you measure these two, and you can show that you need nothing else, then that the black hole has no hair, as we say. Okay, there's nothing sticking out, so to speak, which requires a more complicated description than only mass and spin. Well, then you really have proven that these objects exist. It looks very good, but it does show you in these sort of frontier type basic research themes, sometimes you really have to have patience. You have to have many, many people who work with you over time. This doesn't happen in an afternoon. And the technology, we've improved technology in so many areas over factors of, as I said, 1,000 to 10,000 numerous times. And so, yep, that's the wonderful thing. But it was never frustrating, you see. At any stage, we we came out with a good result. We knew, okay, we'll have to work still harder, still better. But in the end, so that was fun. Still is.
Still is. That's what science is, really, right? It doesn't happen overnight.
Well, I mean, there can be. I would say there are fields of science where you can make one single measurement or one single idea which you might have. I mean, Einstein is always thought to be one of that, yeah? So the idea that, people have about Albert Einstein is, oh, well, he thought, he sat in his room and then thought of a night and then, it's like that. Nah, that's not how it worked. Even Einstein worked, I would say, in total, about 25 years on the theory to get it really done. And actually, to be truthful, he erected the skeleton, so to speak, the house. He didn't fill it with life, in a sense, because many of the conclusions, for instance, black holes, which came out of the theory, he actually was very skeptical that they were correct. So it was not that he did everything. He just did some fraction, and others at the time also contributed. So science is a complicated process with many people participating and contributing. But that's the fun too. I mean, nowadays I would say, look, Poland is part of the ESO. and we're working together, okay? And that's part of a beautiful European international collaboration.
The star you mentioned a few minutes ago is called S2, right? This is amazing. And in the first half of the 1990s, as I understand, two teams astronomers, one led by you, based in Germany, the other one led by Professor Ghez, started looking independently at the orbits of stars about the galactic center. How many years did you and your team monitor the stellar orbits? Really
yeah, okay, so the big problem initially there were 2 or 3 big problems we had to overcome. Number one, I mentioned already, you cannot do this measurement in the optical. Okay, so you have to go to longer wavelengths where you can peek through the dust at the galactic center, which is 27,000 light years away from us. Okay, so you have to look through there. So for that, you need to have sensors, detectors. Okay, a CCD, which you buy or have in your smartphone, it's not going to do anything for you for the galactic center. You have to, so that had to be developed. Number two, remember when you drive your car along a hot road and there's another car in the distance coming at you, then the air is flimmering and the image, the picture of the other star is sort of, wavering. That's the refraction of light as it passes through the atmosphere. And that makes images of stars, even if you take very big telescopes, very, very unsharp. And to get to the best you can do, which is called the diffraction limit, which is actually the ratio given by the ratio of the wavelength and the size of the telescope. The bigger the telescope, the better the resolution in that way. You have to undo what the Earth atmosphere does. Okay, so that was the big second challenge to correct for the disturbances of the Earth atmosphere. That took about 10 years. And well, okay, then the next step is you have to develop techniques to actually measure well, and then you have to have patience. It took us a decade to see these first motions, and then, as I said, then all of a sudden there was this one star which came so close, totally unexpected. Don't have the time to explain that to you, but I mean, from a theoretical point of view, you would not expect a big black hole to have a lot of stars around it. I mean, there can be stellar black holes, as we say, but stars not, because they would be disrupted, okay? And so the fact that there are stars, not just one, we now have about 50 stars, which we are monitoring, which are so close. But initially, we only saw motions, not orbits. Okay, orbits, that came later. In fact, it became clear once we had the motions that to do better still, we would have to get orbits of individual stars, because they really are very precise ways of weighing the black hole. But then you calculated, how long would it take? And then the answer was, I don't know, 100 years, 1,000 years, too long. But then we were lucky. I mean, nature, see, sometimes you have to really hope that nature helps you. And we had a lot of help from nature to give us stars. We now are slowly beginning to understand how they got there. But initially, we didn't even know that they would be there. And in fact, many people said, you can't do that experiment you want to do because, like testing general relativity, because there won't be any stars that close. But okay, sometimes you have to not listen, just go.
Yes, exactly. And a few months ago, I talked with Professor Roger Penrose, and with reference to your and Professor Gez's observations, he said, when I saw those amazing pictures, my first reaction was Kepler was right. I think it's worth reminding our viewers and listeners, Johannes Kepler was a genius German mathematician and astronomer born in 1571. So I would like to ask you, what was Mr. Kepler right about?
Well, you see, there too, I mean, humanity. Let me give you a bit of an allegory to all of this. Humanity, and that's really our, should I say, great feature. There are many bad things about us human beings, but there's one really good thing. We're curious. We are curious. And so imagine you're a curious person and you walk into a forest which you've never seen. And initially you're awed. Wow, look at these trees, big, tall trees. You see there's all small trees, then you see the different types of trees. And that is sort of how humanity started with the skies, right? There it was, the skies, the band of the Milky Way, yeah, and the stars. And you saw planets, and then all of a sudden you see the planets are moving. Ooh. And so the next step, of course, is once you've been awed, the next thing is you develop to become, in that sense, a scientist that sees order. And you want to understand now what's happening actually there. The stars are moving, or the planets are moving. What are they moving, in what direction, and why, and so forth. And then you learn over time. Remember, the Babylonians and the Greeks learned, oh, well, the planets are moving in planar orbits. In the forest, you would basically categorize the trees, and you would see their flowers and all of this, and blue flowers and red flowers. And then comes the next step, and that's the key step for physics. After a while, in the forest, you notice that your blue flowers are always on the left side of the path. Now, it could be chance, you would say, so you have to make a bunch of measurements to be really sure. But once you have counted 100 flowers, and the blue ones are always on the left side of the path, then you either you give up or you become a physicist, because now you have to understand, you have to have a hypothesis. And so in terms of Kepler and all of this, that was the hypothesis that the planets are moving around the sun. Of course, as you know, there was in between the other idea, which was the planets are moving around the Earth. And that can happen, that you have, so to speak, the wrong hypothesis, which then leads to various conclusions what you should be seeing. And then in the end, if you measure well enough, you can exclude the hypothesis that the planets move around the Earth, and you then know they're moving around the sun. So Kepler, in that sense, as a theorist, I mean, you would call him a theorist now, was the one who took the measurements which Tycho Brahe and others had made, and basically put it into a framework of what we would call a theory. Now, that theory was not yet finished. He couldn't really, I mean, he said, well, the planets move around elliptical or circular orbits. He didn't have a justification why that should be. That required Newton. And the concept of a force, and that was being called gravity. But that's sort of the steps how it moves forward. That you're awed by something, then you begin to categorize it in some fashion. Then you find some generalities. Then you have a hypothesis how that might work, and then you test that hypothesis. That's how science works.
You have already mentioned that you and your team, for the purpose of the observations, developed advanced observation instruments that rendered spectacular results. Could you tell us a little bit more about those instruments?
Yeah, okay, so I mentioned there are a number of tasks which were given to us over the years. The first task was we must be able to see in infrared waves. And that was initially extremely difficult because this kind of technology requires sensors, semiconductor devices, which you can't really sort of build by yourself. And this was, in the end, something where we were lucky that the military in the United States at the time had already developed such devices to basically warn the US system if there were rockets coming in. And a rocket you can see pretty well in the infrared, much better than in the optical. And this technology, then we could, over time, transfer into the civilian, especially after the end of the Cold War. It was then possible. Nowadays, we build our detectors ourselves, but back then, that was not possible. Next step was, what, as I mentioned to you, to see sharply with any kind of a bigger telescope required this technique we call adaptive optics. And that really was a main challenge, and again, took another decade to do that. And the next big step was to be able to get what we call spectroscopy, so to basically disperse the light, and so that you can see spectral lines very sharply, and then from the shift of the spectral lines, infer something about the motion. Well, that we wanted to do in an image at the same time as imaging. We call that integral field spectroscopy. So we developed that, and that took also another decade. And next one was the last challenge, the interferometry, so that we can combine telescopes. And so the telescopes which Andrea and we have used up to that point were already the biggest telescopes on Earth, 8 to 10 meters in diameter, but that wasn't sufficient for testing general relativity. So the idea is you combine the light of 4 of the 8-meter telescopes, and thereby you generate a virtual 100-meter telescope, 130-meter telescope. So you see 130 meter is about 15, 20 times bigger than 8 or 10 meter telescope. So that gives you the corresponding advantage in the measurement. So now all of this is challenging enough that you can't do it instantaneously. That's why I have to say I've been extremely lucky, as well as Andrea, by the way, that we are associated with institutions, she with the University of California, which, by the way, I also have been working with for a long time, and I here with the Max Planck Society, who've given me, in the case of MPG, the opportunity to take risks and work on difficult things. And likewise, Andrea, I mean, there you had donors who would give the money to build the Keck telescope and the instrumentation for it. So this is very exceptional. And I mean, you know, if you want to do these challenging things in basic research, you depend on the societies and or donors to give you these resources. And I'm very grateful that this has been the case. And the next thing is then sometimes even a single rich institution cannot do it anymore. And then international collaboration, of course, is the key step.
Yeah, in 2022, astronomers using the Event Horizon Telescope released the first image of the accretion disk around the horizon of Sagittarius A star. I must say, it's truly amazing to me that nowadays we can admire images of black holes, yet the image of a black hole, of course, it's not as simple as it may sound. How are images of black holes obtained?
Well, look, it's in principle absolutely the same thing we've been talking about for the last half hour. instead of planets or stars, also photons orbit a black hole. That is the first statement I made to you at the very beginning of our chat, is that the idea of Einstein was that also photons see gravity. Once you have that statement, everything else follows. Photons may not escape gravity, and photons which travel through space as they go by massive objects like a black hole get bent out of sight. And that was in fact the first thing for which Einstein got famous for, right? He predicted that bending of a background star during a solar eclipse, and said, well, you know, this bending for background stars should be a little bigger than an arcsecond, which was barely measurable. And then there was a solar eclipse in 2019, and in the South Atlantic, and indeed that was seen. That made Einstein the rock star he then became instantaneously. So the same thing you do with the black hole, and it's just that if you go past the black hole and close enough, then it's not just a bending, it actually disappears. And that means when you look at the object, there is sort of a region where there is hardly any or even no radiation coming through. And that is an indication of exactly that. And then the size of this region, which is dimmed, is exactly predicted by the gravitational theory. And indeed, I told you we know the mass to a fraction of a percent. So we know the distance to a fraction of a percent. So we can predict from what we knew what the size of this ring should be. And it came out exactly like that. So that's why the event horizon picture in that sense was a beautiful independent confirmation, and made the case for the black hole, of course, still stronger.
Now for dessert, I would like to ask you a more personal question. I'm always curious about that. How did you become interested in science? Why did you take up science? Was there any particular influence, inspiration for you?
Yeah, absolutely. My father was a physicist, and I early on learned about not only physics, but also about, you know, what is basic research and what needs to be done. I should say that actually when I was 10, 12, 13 years old, what I wanted to become was not a physicist, but an archaeologist. And I still love archaeology. In a way, actually not so dissimilar from our little walk through the forest in the universe, right? I mean, also archaeology is trying to understand the past, very much like astronomy. But yeah, so I then studied physics, and the influence of my father was very important because he was a solid state physicist. I had learned experiments, to do experiments at early age, also mathematical physics, which was advanced over that what we had in school actually. And he gave me very, very good advice what might be future areas in physics that I could go to. For instance, he told me that I was forbidden to go into his field because he said, I'm already there and it's not good that you do the same thing I do. So then he said, well, the Max Planck Society is just starting a new institute in Bonn doing radio astronomy. Why don't you check that out? And so I did. Okay, so that was my first mentor. And my second mentor I've already mentioned to you, and that's Charles Townes. I really, I mean, I owe a lot of how to do science, how to approach it, how far to push it, when to stop. yeah, I went to do something new from Charlie, and he was a great influence on me. That is very, very important. I mean, people underestimate, many young people underestimate how important it is to have good mentors.
Yes, exactly. And has your life, both scientific and personal, changed a lot since you received the Nobel Prize?
Well, yeah, of course. Now, I knew what to expect, since I know many Nobel laureates, but I should say I was lucky and not lucky. The not lucky part immediately was that no Stockholm in 2020. That actually will happen this year. There will be 3 years of Nobel laureates congregating in Stockholm this year. It's going to be a mass production. But so no Stockholm. But the other side was everyone told me, my God, if you get a Nobel Prize, of course the public grabs you. You will have many interviews like we have. You will have to give many talks. You have to travel all the time. And that's why I got lucky, because the pandemic really stopped the traveling. I mean, last year and also this year, each of the 2 last years, I've given 60 talks. And had I been traveling, you know, I would have done nothing else but that. And I still want to do science. And so in that sense, using the medium of these digital media we can use nowadays, in that sense made it you know, easier and left some time left over. But yes, absolutely, my life has changed. I've also found, of course, that it is actually a nice thing, an important thing to do is to, if you can, excite young people. And, you know, it does happen to be that black holes, although they're sort of weird things, are remarkably interesting to a broad set of the public. It's just because it's such a mystery, right? So weird, the idea. And many people, of course, go into this that you can't possibly understand this. It's just not possible. But I think you can, at least some of the concepts you can make clear. And that's a lot of fun, to stand in front of, I don't know, 300 to 1,000 students and try to excite their vision and ideas.
Professor Genzel, thank you so much for accepting my invitation for this wonderful, very, very interesting conversation. And I wish you more and more success.
Thank you, madam.
Thank you so much.
Bye.